Thank you, everyone, for staying late for our talk. And today we will talk to you about the MediaTek Baseband. So about us, we are from Tencent Kin Security Lab, and before we were known as Kin Team. And I'm Marco. This is my Twitter handle. And now I work on hypervisor and baseband, and before I was doing iOS and Android, and I competed in some Pontoon in the past.
Hello, I'm Kira. I'm a security researcher at Tencent King, and I was doing the hypervisor before last year, and now switched to the baseband. And I also play CTF on my spare time.
So we are from Shanghai, and this is our blog and Twitter if you want to check it out. And we are White Hat security researcher inside the Tencent. So this is what we will talk about today. I will do the first part of the talk, which is the less interesting one. And then Kira will do the more interesting one, which is the second part about the MediaTek baseband. We will talk a little bit about the previous work on this modem. Then a little bit about the networks from second generation to 5th generation, and in particular 5th generation, since it's a popular topic today. And then we will give an overview of the baseband in a generic way, and then we will cover the MTK baseband in detail. So there is some public work about the MediaTek modem. The two main public research are this talk by Charles, Nitai, and Anna, which is called Understanding and Debugging and Attacking the MediaTek Communication Processor, which gives you a good overview of the modem and its internal structure. ComSecuris also made a blog post, but this one covers the attack surface from the modem to the application processor, and in particular how to escape the modem to run code on the application processor with a bug. So there is no much public material on MediaTek actually, unlike, for example, more popular platform like Samsung Shannon. Going outside the MediaTek, there is other research on the modems. Here I list 3 of them. The first one is from ourselves, from KinLab, which covers the Huawei modem. It's a talk that we give at Black Hat, and we exploited the Huawei baseband with a memory corruption bug. For the Samsung platform, I recommend the talk by Amat, which covers everything about the Samsung modem plus memory corruption bugs. And for the Intel baseband, ComSecuris made a very good blog post if you want to check it out. So why we started this research? Last year we got a contract with a vendor to improve the security of their modem. So we did this kind of research for them, but previously in our daily job we were already familiar with the MediaTek modem because we check pretty much every baseband. At the end of this contract we disclosed to this vendor a bunch of bugs, and they fixed them. And this talk in this talk we will cover our work on this platform, and especially how you can start your own research on this modem. And recently we switched to do some 5th generation project with other vendor. So why it's interesting to check the MediaTek platform? The MediaTek platform maybe doesn't run on the high-end device, but it still have a significant market share, especially on medium and low price device. I found an article online estimating that the market share is around 11%, and recently it became popular also in Europe with some Samsung Galaxy models. which they run the MediaTek system on chip and the modem. So let's check the network really quick to get everyone up to speed. I know in the audience there is maybe people that took the baseband training, so but still we have to cover a little bit the basic before checking the MediaTek baseband. What is a baseband or a modem? It's basically a set of hardware components which runs a firmware, and they implement a set of specification conforming to a cellular network specification. So they have to do it in order to speak with the network and decode the messages. We have several generations of cellular network. They are commonly referred such as second generation or fifth generation. So one very important topic of mobile network is authentication, because all the generation, such as second generation and the 2.5 generation, the mobile phone or the device will not authenticate the base station. So it's possible to impersonate a malicious network in these circumstances and exploit or send malicious data to the phone. Starting from the third generation, which in this slide is from UMTS, there is some form of authentication for the phone to verify that they are speaking with a legitimate base station. But not all layers are authenticated, so there is still room for attack surface. Like most popular network stack, such as, I don't know, common internet protocol, the mobile network protocol are also layered. So you can see on the right side Aussie model with 7 layers, and on the right side there is a picture for the GSM, and you can see they also have a physical layer, data link layer, and a network layer. They don't perfectly match, but you can still have an idea. So basically, the higher you go into the layer, the higher the complexity, and this is similar, for example, on a traditional protocol. If you think about, I don't know, TCP and full HTTP web application or something like that. So complexity and most interesting bug, often they are found in the upper layer, like layer 3. About 5G, let me spend a little bit of more slides. And why now there is all this hype about 5G, and why 5G exists, basically. So until 4th generation, basically the goal of the carrier was to get everyone connected and give you high bandwidth and enjoy rich content and fast download. But now, I mean, everyone has a smartphone and a laptop, so there is not much room for growing. So 5G, the focus is a shift, and the focus now is capacity and the chip radius. So basically, now the plan is to connect everything, the car, the device, the sensor, and the IoT market. So for 5th generation, there are several big players. Some are ahead, some are a little bit behind. Of course, there is Huawei, which is pushing 5G very hard, and Qualcomm, and then other players that are kind of catching up. And 5G will also have a role in critical infrastructure, because the expected capacity of this kind of network will be 1 million objects for a square kilometer. And so with this kind of number, you cannot expect the consumer to be end user. In 5G, you will have object consuming the network, so you will have robots, cars, surveillance equipment, city management. And this will impose also some reliability requirements, of course. And because in 4G, reliability, of course, is important, but it's not critical. So you will basically switch from something consumer level to something else. And not only smartphone will be connected. Of course, in this talk, we will mostly talk about smartphone. But in the next few years, I think the baseband research will expand to even more interesting targets, actually, because more and more device will have a modem. So right here in the picture, you can see there is some PCI Express modem that you maybe find in a car. So this kind of deployment require different approach. So 5G will have to satisfy different type of goal. You will have a different deployment based on the different type of property your network will have. You can have enhanced broadband, which will bring faster data consumption. So basically, it's improved 4G. But then you have also another mode, which is URLC, which is for mission-critical application that don't care much about bandwidth, but they cannot afford delay or unreliability. Think about some network of industrial robot. And another example is machine-to-machine deployment. So currently we are working on several 5G devices. Huawei, of course, which is pushing 5G, so their firmware have 5G network stack, the phones, and some Wi-Fi router. Then there is the Samsung Note 10, which came out recently and have the 5G stack by Samsung on the Exynos platform, and some Qualcomm devices. The problem with 5G research is that there is no completely ready solution, and there is this project from Eurocom, which they are trying to build an open source stack that can run with a USRP. And they are still developing, and we are actively tracking, and we hope we can contribute in the future. So before leaving the stage to Kira, I want to give some tricks to set up the baseband, the base station. And I think the best solution is probably to use Docker if you can, and because if you use a virtual machine, you will have to use a virtualized USB controller, and this will introduce delays. And software-defined radio are very sensitive to delays, as you can imagine. So instead, with Docker, you can just forward the USB bus inside, and your staff can directly talk with the SDR. And also, it's useful to keep separated the environment for the base station, because often this kind of software require a lot of strange dependencies, and some of them are even requiring kernel modification. So it's better to run in a standalone machine. So I wanted to summarize in a slide how to attack the baseband. You need two ingredients. The first one is a mobile stack software. It can be OpenBSC, OpenBTS, or SRLT. You will modify this software to send your exploit over the air. Then you need some hardware, which can be SDR, for example, the USRP, BladeRF, or a Lime SDR, or some custom hardware, like we demonstrated in our Black Hat talk with the Huawei baseband. We used a CMU 200, which is a mobile radio testing device. These two components will modulate the signal over the air, and hopefully you can trigger your exploit, your bug, into the baseband. This picture is a summary of mobile smartphone. because now a mobile phone is not anymore a single CPU and some RAM and memory executing software. Now these kind of devices are more and more complex. You have at least 3 CPU on it. The first one is, of course, the application processor, which runs Android or iOS. Then you have the baseband processor, which is the modem, which we will cover in this talk. And then you maybe have a Wi-Fi system on chip. And the baseband handle the mobile network, so 2G, 4G, etc. And this kind of component can be attacked remotely. So what I want to stress is that even you get code execution inside the baseband, you cannot influence directly the application processor. So you still need another bug in order to escape the baseband, let's say, and execute code on the application processor. Still, from the baseband, you have limited capabilities, but still interesting, since you are in a position that you can collect call data, message data, and internet traffic. And these 2 components, the application processor and the modem, they communicate via several means. For example, shared memory or PCI Express or even USB. And the most interesting part is that the baseband currently they lack of the most modern or even basic mitigation. So they are attractive from an exploitation point of view. Usually exploiting a bug is straightforward. So I will leave the stage to Kira, which will present the work on the MediaTek.
Okay. Hello, everyone. I'm Kira, and I will talk about the MediaTek baseband. First, there are some necessary components of a baseband. I list 4 of them here. The main part of a baseband is the RTOS, which, if we mention the word baseband, we are mostly talking about this thing. And the baseband may based on the RTOS like ThreadX, VxWorks, or some other similar OS. And in TEOS, there are some handlers or modules to deal with the baseband. One of those jobs is loading the modem image when the phone boot up. The TEOS will decrypt the image if needed and load it in the memory and set up other things. The kernel will also join this procedure. As far as I know, the start is kernel invoking the TEOS command. In kernel, it will also register some devices to do the communication jobs. So is the user mode binary. Most of the above things are attackable, which depends on your target. And the most common target is, of course, the first one, which you can attack over the air. It's really cool. And in general, baseband research is relatively small area in which not many people doing studying it. So I come up with this page to speed up someone who wants to start. The first thing is to read the previous work by others, which is like you are standing on the shoulders of giants. And the second is to download what you can download from the network. There are innumerable sources online. You can even find the source code of a baseband, like a Huawei baseband, which is leaked years ago. Next is to extract the firmware from the target phone. This can be a difficult step or just an easy win. After you got the firmware, you can start your reverse engineering and bug hunting. In this process, you may need to learn the 3GPP technical specification, and this step can be very boring. But be patient. Knowing the target more, the chance you find a bug is higher. And like a Huawei, MTK also has some leaked things on GitHub. There are parts of source code and some object files and libraries. There are old ARM versions years ago. This will be very useful for bug hunting because the binary is with symbols. But for sure, you still need the firmware of the target. Also, this is helpful because the libraries can be linked together with your own code in a binary instrumentation environment such as QEMU. For this part, I will talk about it in detail later. Next, let's do a quick view of the architecture of MTK Baseband. There are lots of functional tasks took over by the RTOS, including the CM task, which is connection management, the MM, which is mobility management, RR, which is radio resource management. As the picture shows, there are many tasks. And the AP and the CP also use AT commands to communicate. They share data with each other within the power of shared memories. And the most special part is the CCCI, which is short of cross-core communication interface. It is implemented in the kernel. Basically, it did the job to connect the AP and the CP. So it's not a similar conception as the former two. It initializes the UART lines, which are mostly used to transmit AT commands and some audio data. It also sets up the shared memory and divides it into several regions. Okay, let's talk about how to get the firmware. So I assume you already have the root permission on the target Android phone. The firmware is available at the directory dev block by name. In this place, you can get most of the things you need. And for the kernel, the name is boot, and I recommend this great tool to you, which is developed by our colleagues. It can help you load the VM Linux image in Ada Pro. Then for modem, the name is MD1 image. At least on our phone, the firmware has no encryption at all. After you get the modem image, you still cannot just start your reverse work because the image has some type of format. It consists of many small sparse image. You need to extract them from the big image. And we found the definition of the format in the online source. And I made an 010 editor template to visualize them. Each of the image inside has a header, and the name field is also in it. The most important two images are the MD1 ROM and MD1 debug info. MD ROM is the code, and MD1 debug info is the debug symbols. And there's a little story about the ROM. Because all the online leak of the firmware are the ARM version. So we take it for granted that the image is ARM, but the ADA disassemble result shows nonsense. So we thought it's encrypted at first, but one day we accidentally loaded it with the MIPS CPU type. It shows some reasonable results, but still not all proper. At last, we figured out is the MIPS 16E2. And what is MIPS 16E2? In short, it's the MIPS 16E with additional improvements. There are some extended code, opcode, and unfortunately, AdaPro failed to disassemble the new instructions. For example, I list of two of them here, the MFC0 and MTC0 code instructions. So we wrote some tools to help us reverse. Then finally, we can start our reverse. The first thing to do is loading the symbols from the debug file I mentioned earlier. The file exists not only in the image, but also on the SD card. You can see the name in the image is MD1 debug info. We guessed the format at first, but the format is not very complex. Also, there is previous work on it. So we wrote an Python script to recover symbols from that file. After that, when I rendered the liquid source of MTK, I saw a Perl script in their debugging suite. And the format is explained in detail in that script. So you could save some guessing time with this. Then we need to fix the segments in AdaPro. And here is our result. The address might not be very accurate because we can't tell what is exactly the end or start address by reverse engineering. There is a good tool to help find the base address of a firmware, and it's written in Rust, and it works perfectly, at least for our firmware. So I recommend it to you. After all the previous work, we can start auditing the code now. The entrances of incoming message handlers are good candidates because and the task main I mentioned before will call into them. Now I will take one of the tasks as an example to demonstrate the real code. And this is the task main function. It's very typical of an RTOS system and other modems also have some similar tasks. The code is running inside an endless while loop. It will wait for a new message to come and dequeue the message, then construct the ILM structure, which is the interlayer message structure. And the pure buffer PTR in it is where the real data stores. Then the last steps is to handle them with the main. Okay, let's dig more into the task. After we entered the main, we can see numerous message handlers switch cases depending on the message ID. The state machine in the baseband is very complex. So if you want a specific message handler, sometimes you may look into very deep inside. However, we can look for a message name in the specifications like 3GPP 24.08. Then search the method name in AdaPro. The picture here shows how the MMPO TMSI realloc command handler is called from the main. And with our eyes, we found some bugs in the baseband. But we all know that for this type of things, it's very difficult to run it perfectly on our own computers. So emulating the whole system is too hard for us. But it's not that difficult to emulate part of the code. And I think the target function requires two of the following. One is complex enough to father. It can't be too small, or with our eyes is enough to audit. And second is know of very few IPC cores, because emulating IPC cores is troublesome. It may need lots of work to do. Then the decode and unpack function catch our attention. For example, the MCD unpack, which I will talk about later, and the ASN1 decoder. They don't have any IPC communication. So the method is very easy. First, write a C wrapper to call the target functions. The wrapper does the preparations like before the function call, such as read the input from the stdin and initialize some all the structures. Second, maybe this is the most time-consuming step. You should write the makefile to link what we need. As I said before, there are liquid source code and libraries online. So our work is mainly based on that. At last, using the AFL QEMU mode to do the fuzzing. After you fuzz a while, you may get some crashes. When you want to test your POC or something else, you will need to see the log files. There is a crash alert in the dmessage by the CCCI interface. But this is just a very brief summary of the crash. So for more details, you need to check the log files on the SD card. the files are shown here when a crash happens. But sadly, the MTK makes a very special format for the log files. We are not able to read the log directly because it's some binary format. And they are logged by the DHL trace and many other similar functions. They will record the modem ID, what function is called, and much other information. We did little research on the format, so if you want to know more, just go to reverse the DHL functions. Another thing is that you can capture the log even the modem is not is running normally. The method is easy. Just dial this 800 number and click the log kit, then start to record. Okay, now let's talk more about the MCD unpack. This function is very important because it is the first unpack function before any further process of the message. Nearly every message is handled by it first. The message format uses the BER encoding, BER, which is short of Basic Encoding Rules. It is the set of rules for encoding ASN1 defined data into a particular representation for transmitting to another system. And the most fields inside the message are TLV, which is type, length, and value. Sometimes may have end of contents. The function process the data as a bit string. And we fuzzed this function and got some crashes, then reported to the vendor. After that, we studied this function. The first argument of the function is the message ID, which will decide the sequence of opcode to be used in the MCD unpack run. The function works like a CPU, which means it fetches the opcode first, then does the work according to the opcode. There are many types of opcodes, like choice, call, case, and so on. One special opcode I need to emphasize is the max bytes. This is the length check in the decode stage. So most of the memory corruption bugs are killed in advance by it. When we thought we found a bug to do the test, but the modem won't crash by any means. At last, we figured out it was this function to prevent the bug. So after all the theories, let's see some real vulnerabilities. This bug is in the EMM attached accept message. When the code is decoding the emergency number list, the structure is shown in the picture. It doesn't check the index of the current emergency number. So this could lead to a heap buffer overflow. Another problem is that there's no check on whether the source message is big enough. For example, we send a 20 bytes message, but we fake the length is 200. Then we can read out of bound on the heap. Another bug is in the activate PDP context accept message. The vulnerable field is protocol configuration options. if you have ever watched the Amat's talk on the Samsung Shannon baseband, you will find our bug is very similar to his. When the code unpacks the config option, it will first decode all configs length and store it in an array on the stack. So we can send many zero-length bytes to fill the array. Then we are able to modify the return address since no stack cookies at all. Okay. We are not required to exploit the baseband in our business project, so we just wrote a POC about the bug. Our environment is shown here. Our OS is Ubuntu 18.04. We run the OpenBTS in the Docker, and the device is USRP B210. As this bug, we don't need much work to set up the state machine. So the POC is very easy. Just find the corresponding class of the message. In our case, it's the L3 SM message activate PDP context accept. Usually, each message has a corresponding class in the code. Then modify the write body method in the class. In our case, I just simply modify the size field and the data to write. And then OpenBTS will do all the rest of things. Okay, now let Marco give us some summaries.
So, as Kira showed you, in that particular bug, the modem still lack of any modern baseline mitigation. And it shows you that in particular case there are no even stack cookies in function performing copies on the stack. So you can imagine that the other more advanced mitigation are not there, of course. And to conclude, we would like to thank this particular vendor which we cooperate with, and MediaTek, because they were very fast responding and very friendly also, and they were open to discussion and feedback, and we had a positive experience in this contract. So this concludes our talk, and if you have any question, please let us know.
Thank you for your talk. I have a question. Could you tell any details about how you load an RTOS to QEMU and run AFL fuzz on it?
Okay, so actually we didn't run the entire RTOS. As Kira mentioned, there is a leaked source so object file online. So we just recompile those into a Linux ARM ELF, and then we run that one to fuzz. But you could run the entire baseband if you emulate some stuff, or maybe if you remove some non-important task from it. But we didn't choose this route for the amount of work required. We didn't have much time to do it.
Okay, thank you.
No problem.
So for the firmware you were exploiting, do you have something like a build date so that you can make kind of a history of mitigations or stuff? Because, for example, for Broadcom, you can see like in the S10e, there is the first mitigations in the heap for Bluetooth and Wi-Fi. Is there something coming up like this for MediaTek?
I'm sure you can extract the version from the firmware. I should check, but we didn't check the further updates. We should follow up with the vendor because I mean our contract was with a vendor, not MediaTek itself, so they have limited influence on the development.
Any?
Hi. I'm curious about whether you checked if you were able to patch the baseband or if they had some integrity checking, because I know that a few years ago they didn't check the integrity, so you can actually like inject patches to make instrumentation a bit easier, but it was a specific phone as well, so I don't know.
We didn't try on MediaTek because we didn't need it for our particular assessment, but I believe probably they do, at least at the load time, probably they do some
Okay.
check, yeah.
Oh, thanks. I'll check.
Thank you.
More questions? Okay, doesn't seem so. So thank you.
Thank you.